Hello everyone and thanks for coming. I'm Matias Vara and I work at Huawei France. In this presentation I'm going to talk about the deployment of microservice as Microvm total guest. I hope you enjoy the presentation. Before I go deeply into the presentation, I would like to picture what is a microservice. Roughly speaking, a microservice is a way to decompose a monolithic application into simpler components named a service. Each service provides a functionality. One possible way to deploy microservice is by using virtual machines. This pattern is called service instance per VM. The deployment of microservice as virtual machines has mainly two benefits. First, it allows to isolate microservice. This means that they can't interfere with each other. Second, you can leverage on cloud infrastructure like Amazon Web Service or Google Cloud Engine. So let's see how is the actual deployment of a microservice by following this pattern. I'm going to describe the picture from bottom to top. We have a bare metal host which contains an operating system and the hypervisor. In the context of each virtual machine, we have the device model which is created by the virtual machine monitor, which could be QEMU or Firecracker, and the microservice run as a user application on top of a general purpose OS. Let's see what are the features that a general purpose OS provides. Generally speaking, our operating system has a scheduler, file system, networking, and some drivers. There is a separation between user and kernel space, and the microservice executes as a user process with its own memory space, and the communication between user and kernel is based on syscalls. However, a general purpose OS consumes a lot of resources like memory, CPU, and on-disk mesh. Also, the creation and storage of this sort of VM is complicated. For example, if the image is deployed in different cloud providers, different drivers should be packed. The reason is that, for example, the device model for Amazon Web Service is not the same as the Google Cloud Engine. And also, the VMs take too long to be up and running, which makes it hard to implement continuous integration and deployment of microservice. So the result of consuming so much resources makes that we can only host a few virtual machines per host, and in addition, the maintenance of these VMs is high. So to reduce the complexity of a general purpose OS for a dedicated task as microservice, and at the same time leverage on the strong isolation that virtual machines provide, some approaches propose the use of a unikernel to host microservice. A unikernel is when you compile the kernel with the user applications. Currently, there are different unikernels which are used in different scenarios like OSV, MirageOS, Unicraft, NanoVMs, etc. In these approaches, the kernel and the application share the memory space. The kernel code and user code are combined into a single binary, and in most of these approaches, there is no separation between user space and kernel space, no context switching, no paging, and the syscall are just calls to kernel code. However, the port of an application takes time and effort, so sometimes the unikernel must be redone for each new application that needs to be ported. So in this context, Toro is a unikernel that provides a minimalistic API to develop microservice. I'm going to present Toro in the following slide. So Toro is an application-oriented kernel which provides a minimalistic API to provide applications. The unikernel is mainly made of 5 modules. So for example, the thread unit allows the manipulation of thread, the memory unit allows the allocation of memory. The whole kernel is about 18 kilolines of code. So to get better performance on KVM, Toro focus on virtual I/O devices, and the networking support both blocking and no blocking socket interface. So in Toro, the user application and the kernel compile together, and the user application has to explicitly define what are the components that must be included. To define this, the developer must explicitly specify the unit that must be added by using the keyword use. So the resulting ELF binary contains both the kernel and the application. And this binary is immutable in the sense that you can use the same binary in different hypervisors without modifying it, thus simplifying the maintenance of the microservice. Then we use a script called Cloudy to create VMs in different hypervisors. But let's see how much work is needed to deploy an appliance like a web server by using Toro, and how much work is needed. To illustrate the amount of work to deploy an appliance, I'm going to use as a running example the web server appliance, which is a simple microservice that serves a file by using HTTP. This appliance is currently used to host the Toro website. So in terms of code, this appliance needs to get connection from the internet and be able to read files. So it needs to include a network driver and a block driver. And in addition, the appliance needs to include a file system like FAT or extend, and also the TCP IP stack. So the microservice has to be compiled with this code. In terms of device model, we need to set up the devices that the appliance is going to use. So for example, in this case, the device model must include a Virtual network core and a Virtual block for block devices. To deploy the appliance, two undecim files are needed. First, the binary that contains executable code, which is an ELF64 binary, and the files that the appliance hosts. Generally speaking, the binary is about 250 kilobytes, but the files could be in the order of megabyte or gigabyte. And finally, to provide networking for the VM, we need to set up, for example, the IP of the VM, but also the IP of the host. In addition, to expose the VM to internet, we have to set up some sort of IP forwarding, for example. So let's summarize the main drawbacks of this configuration. First, this image consumes memory and on-disk space. For example, each guest has its own image. This image has to be distributed in all nodes. The use of a TCP/IP stack requires configuration like bridge and EP per guest drivers, devices. Also, the use of more devices increases the attack surface. Sharing of files between guests and hosts is most of the time hard and complicated, and relying on a specific file system in the guest is not good for immutable image. So the question was, can we do better? And when I said, can we do better, I mean, can we simplify the configuration steps? Can we reduce the attack surface? Can we still provide a reliable shared file system? Can we reduce the VM CPU consumption and footprints? So we propose to tackle this issue by providing a cloud infrastructure in which VMs are micro VMs. Networking and file system in the guest is implemented by using Virtual vSocket and Virtual FS, and a distributed file system is implemented by using CF. In the following, I'm going to briefly present these technologies and explain how they were implemented in Toro. So Virtual FS and Virtual vSocket are both virtual devices. Different than other devices, they are in-kernel devices, so they are more performant than emulated devices. I'm not sure about Virtual vSocket, but in the case of Virtual FS, it is in QEMU since 5.0. In the case of Microvm, it is a minimalistic QEMU machine, which is inspired by Firecracker. It provides several benefits like reduced device model based on Virtual, improved booting time, and reduced footprint. So let's talk about a bit Virtual FS and Virtual vSocket in the context of Toro. VirtualUFS is a virtual device that allows to share a directory between the guest and the host. In the guest side, you only need a VirtualUFS driver. The device is supported by Microvm machine. The only requirement is that the driver has to support the virtual MMIO transport layer. In the host side, you need a daemon named VirtualUFS-D, in which you have to set up what is the directory to share and a tag that is afterward used by the guest. The use of VirtualUFS has several benefits. For example, we don't need to base on a specific file system. This means that the binary can be immutable. The configuration for VirtualUFS is minimal, so you don't need image anymore. The unikernel source code and architecture can be drastically reduced. For example, the virtual file system becomes a driver for VirtualUFS. You can remove buffer cache, file system driver, and block driver, for example. In the case of virtual vSockets, it allows to establish a POSIX socket-based communication between the host and the guest, in which each guest has a context ID to be identified. So the use of virtual vSockets has several benefits, like simple configuration on the guest, no need of TCP/IP stack, no need of virtual net, etc. In case of you want to expose the virtual machine to internet, you need some sort of proxy to forward traffic from internet to the guest. And the last piece in this architecture is the shared file system. To allow all nodes to access to a common file system, we built a CFFS cluster, and we use it to provide the binaries of the VNs and the files. I'm going to talk a bit about this cluster and how it has been developed. So to try this architecture, I built a 3 nodes CF cluster. Each node participates with 10 GB of disk to the cluster, and I use the public cloud OVH. Each cluster is a 2-core with 8 GB of memory, and the cost of each node is about 16 euros. To deploy the virtual machines, I rented 2 cheaper nodes. These are 1 core and 2 GB of memory hosts that cost about 3 euros per month. In this machine, I mounted the CFS file system, and the cluster has been used to store binaries for the VNs and the files that are served by the microservice. The host client 1 and client 2 are used to deploy the microservice. To ease the creation of virtual machines, I installed an open source project on these machines named XML-RAD, which allows to automate the launching of VMs. So for example, to ease the forwarding of ports, to launch VirtualUFS and so on. So I have some results about evaluation of the architecture. So the binary side, which is the binary that includes the kernel and the user application, has about 235 kilobytes. The time to review the microservice is about 500 milliseconds, which is the compilation time, and it is the time that's going to impact the ability to do continuous deployment and integration of microservice. And the boot cycle, which is turning off and on of the microservice, is about 80 milliseconds. And just to have in mind that an echo hello world takes about 2.5 milliseconds. And other important factor I was interested in was the CPU usage. In this case, the VM consumes 90% of the CPU when it's answering a request, and then when it's completely asleep, means that the core is halt or the VM is halt. It is taking about 100% of CPU. And the memory footprint per VM is around 2.9% of memory, which is about 60 megabytes, or 35 VMs per host. In this case, I have compiled QEMU with all the configuration enabled. And just to have in mind that the whole cluster, it costs about 58 euros a month. So it makes that you spend about 85 centimes euros per month per VM. And I have also uploaded all the scripts and the tutorial to create your own cloud based on the configuration I just presented. So in the following, I'm going to show a video that present the implementation of this architecture. So what we see here is first is the dashboard of TF. We can see we have 3 nodes. And as I said, each one contribute with 10 gigabytes, would make 30 gigabytes of total of the whole cluster. Then we have XML RAD, which is the tool that's we are using to ease the deployment of the VM. So for example, here we have the 2 nodes and the static web server microservice. We have some parameters like the binary and the file system that is shared to the host, and also the forwarding of the port between the host and the guest. We can also have the output of the screen if we click on the WebSocket. So this is the screen of the VM. It could be compiled by using headless, but in this case, I just compile with the screen. And this is the total website that I'm going to refresh just to show that the VN and total is correctly answering. So for example, if now I'm refresh, we're going to see that the screen scroll up. I'm going to do it again since it's not really evident. But you can see that the screen move up. And now I'm going to just get a picture and see that it's correctly output in the VM. So yeah, well, this is one of the challenges that I face and I'm continually facing at the moment in order to improve the deployment of this architecture. First, I would like to improve the support for live migration, which is not currently supported by Microvm machine. Also, I see that we have a sort of bottleneck when we have to forward traffic from internet to the guest. So we have to improve the way we do it in that case. I think we can improve the overall performance by using zero copy when we use virtual-IFS and virtual vSocket. This is more in the guest side, in the drivers, in the total drivers. And I think current evaluation of this architecture should be improved by comparing with approaches like unikernels, containers, and also general purpose OS. All these challenges remain as a future work. So, well, I finished the presentation. So if you have any question, feel free to ask. Thank you very much.